shapes in the way that I've drawn them. Remember, the focal length is the center of the radius of curvature. Or excuse me, is half the radius of curvature. All right, I'm going to stop at 45. All right, good. B is right. Because you can imagine that these are parts of bigger spheres, right? And this sphere is not really big. But this sphere is actually, that's not really circular, but you get the idea that it's cut from a much bigger spherical shape. So then, what do you think the focal length for a flat mirror would be? If this one, which is fairly curved, has a small focal length, this one, which is less curved, has a bigger focal length, for a flat mirror, what do you think the focal length would be? Infinity, right. So the focal length of our flat mirror is going to be infinity. And so we can think about the mirror equation, 1 over infinity equals 1 over p plus 1 over q. Well, 1 over infinity, that goes to equal 0. And so out of this, I can get, for flat mirrors, that p is equal to negative q, which is what we know already, that the object distance is the negative of the image distance. Remember, because the image distance, it's a virtual image, and virtual images always have a negative image distance. That's why we have this negative here. Okay, so some guidelines for the signs. In this test on mirrors, it's very important that you get the signs correct in working the problems. Because if you don't get the signs correct, then it's going to mess you up on getting the rest of the answer correct. So just a few little guidelines. The object distance, as far as we're concerned, the object distance is always going to be positive. We'll see with lenses that there are some cases where we can have an object not in front of the mirror, but we can have it behind the mirror. So as far as we're concerned, the object distance will always be positive. But that'll change when we move into the lenses part. So this will always be positive. The image distance, if the image is in front of the mirror, that means it has a positive image distance. Now remember, a plus q means that we have a real image. And that means that it can be projected onto a screen. So, if I have a mirror and I have light shining onto it, if I put a screen back here, I'm never going to get an image on a screen back here from that mirror, right? Like, this doesn't have anything to do with the mirror back here. But if I put it over here, I'll be able to create an image on a screen. Next time I'll bring an actual mirror that produces a real image. It's kind of cool. I forgot to bring it today, but I'll bring it next time. So if I'm in front of the mirror, that means my image distance is positive. Goodness, bless you. If I'm behind the mirror, was that you? If I'm behind the image, if I'm behind the mirror, it's a virtual image. I told you about my wife. She sneezes like a champ. Have I told you all this? Like very loudly, I mean. Not like a champ, the opposite of a champ. It hurts my ears. And when we first got married, I said, I'm sorry. It's just, every time you sneeze, it just hurts. Because it's just the right frequency to hurt my eardrums. And so for many years, like she stifled her sneezes. And I just learned this. And now I feel bad, right? Because it feels good to let out a good sneeze, right? So I've told her since that it's okay, like I'll endure through the pain, you can just go ahead and sneeze. But usually I think she just tries to go away and sneeze, but you can't always help that. Anyway, the virtual images, where are they? They're behind the mirror. It's like in that really bad movie Poltergeist, like the crazy mirror people, they're all behind the mirror. They're like virtual people. And so they're behind the mirror. These cannot be projected on the screens. Now for focal lengths, if my focal length is in front of the mirror, then it's positive. Is that going to be a convex or concave with my focal length being in front of the mirror? Think about it. Think about the shape. Don't answer just yet. But think about the shape of the mirror. Is the radius of curvature half, or is it going to be concave or convex? Which is it? Concave. Concave mirrors have a positive focal length. Convex mirrors have a negative focal length. We'll see this as we work through problems. But do you think I'm going to tell you that the focal length is positive or negative? Like, do I look that nice? No. No. So you need to know that concave mirrors have a positive focal length and convex mirrors have a negative focal length. Don't worry, we'll see when we work through the problems that we'll see with practice you'll get it. But knowing these signs is pretty important. Here's a sample problem. So I have a concave spherical mirror. There's the radius of curvature. That's where the object is located. I want to know what is the magnification. Couple equations for you to remember here. Your mirror equation, 1 over F equals 1 over P plus 1 over Q. And then also you need to remember that the magnification is negative Q divided by P. Goodness, bless you. It's room, isn't it?
Is that why you're scared on this?
I'm not scared.
We always say goodness for me, but I'm not Alex.
Did you just sneeze? All right. Let's do 150. Okay. Try to shoot for 150. We're looking for the magnification. All right, let's stop at 205. 205. Just guess if you're not sure. About 2 more seconds. Listen, there's some homework here to help you practice this. Although looks like y'all got it pretty good. Some are more difficult than others. All right, some of these problems, and we'll look at some that are more difficult. This one's a little bit straightforward. So let's take a look at how we do this. I first determine what is my focal length. Well, I know the radius of curvature is 20, so that means my focal length is 10. And I also know that it's concave, so that means it's positive 10 centimeters. We can just keep everything in centimeters. We'll keep the units all throughout. And then it tells me that the object distance is 20 centimeters. And now I want to know what the magnification is. So first I say 1 over 10 equals 1 over 20 plus 1 over Q. That's my mirror equation. And that's 2 over 20 minus 1 over 20 equals 1 over Q. So Q is equal to 20. And then I say, what is my magnification? My magnification is negative Q divided by P, and that's equal to negative 20 divided by 20, which is negative 1. So my magnification is negative 1. That's very good. C is right. Hey, do you know how many tickles it takes to make an octopus laugh? 10. 10 tickles. Okay, let's try this one. That's hilarious. A little more thought you have to put into this one. Don't forget we had two expressions for our magnification, not just negative Q over P, but there was something related to the height of the image, height of the object, something like that. All right, let's stop at 150, 150. Seven more seconds. I'll go to 155. 150. All right, 2 more seconds. All right, I think B is, where is it? All right. Yeah. Okay, so what you have to do here is first determine the magnification. But remember, my magnification is not just negative Q over P, but it's HI over HO. So the height of the image is 5 centimeters. So 5 centimeters is the height of the image, and it's a 2 centimeter high object. And so that's equal to 2.5. All right. Now the object distance is equal to 3. It's going to be positive 3 because that's all that we're going to have for this test is positive image distances, object distances rather. And it tells us that well, that's all it tells us. And so now I want to know what is the image distance. I know that M is equal to negative Q divided by P. And so this is 2.5 equals negative Q divided by 3, and so it's minus 7.5. We should know that it has to be negative, right? So if we came out with a positive number, we should know that the image distance has to be negative. Why? Because it's a virtual image. So sometimes you'll have to look for clues in the problem to tell you about the various signs. So in this case, you didn't have to do that. But you should know that the image distance is negative because it's virtual. I think there's one more here. Listen, there is a problem in the homework that requires you to solve a system of equations where you have to solve, like plug one equation into the other. You're not going to have to do that on the test, okay? It might be useful for you to step through that problem, but you're not going to have to do that level of algebra on the test. Is that a joke worthy? No. No. Here you have a convex mirror. Give its radius of curvature. I want to know the magnification. All right, let's stop at 155, 155. All right, good. 155. Okay, look. I know that I can get rid of some answers because it's a convex mirror. Which ones can I get rid of? Convex. So what does the positive magnification mean? No. Well, no, sorry. I actually let me cover something. I don't know that y'all really know this just yet. It's not necessary. We'll go back and work this problem. It's not necessary, but it's useful for you to know. Well, it might be necessary for you to know the different types of images that different types of mirrors produce. And we're going to do that with the ray diagrams next. Like you'll be able to practice with that. But let me just sort of summarize it here, and then we'll go back to that problem. So with convex mirrors, this is your mirror, this is your object. The image is always virtual. The image is always upright. The image is always smaller. It doesn't matter where you're standing. You're always going to be virtual, upright, and smaller. In fact, if you think about it, upright images are always virtual. Let me write that up here. Upright images are always virtual. Because, you know, our magnification is negative Q over P. If I have an upright image, that means its magnification is positive. So Q has to be negative in order to make that positive. So convex mirrors produce that kind of image. Concave mirrors are a little more complicated because you can have three different types of scenarios. You can have outside the focal point, there's my object. You can have inside the focal point, or you can have at the focal point. When I'm outside the focal point, I produce a real inverted image. When I'm inside the focal point, I produce a virtual. And did you know virtual images are always what? Upright. So it's a virtual upright image. It's also bigger. And at the focal point, there's no image at all. Who wants to look at themselves on the concave mirror? Olivia, how do you look? You're upside down. At some point you get fuzzy. Are you fuzzy yet? Are you fuzzy? Okay, so now she's at the focal point. Okay, so the focal point is about that distance. Can you see it?
I can see my hand, but I can see the rest of you.
Are you fuzzy? Can you see it? Is that hurt you?
I see him.
Well, now.
Yeah, that's good. Very good smile.
Okay, Tyler, can you do it? Okay. You're upside down or what? Can you see yourself? Are you upside down? Alright. Tell me, do you get fuzzy at some point? Are you fuzzy now? Are you can't really see an image of yourself? Okay, now watch when you get really close on that. Huh? So now you're right side up, right? Are you bigger or smaller? A lot bigger, right? This is sort of how I see myself. So that's how we have here. When I'm outside the focal point, I have a real inverted image, and that image is actually, I'll do the images in blue, that image looks like that. When I'm outside the focal point, the image looks like that, right? And over here, I get no image at all. It just looks fuzzy. Okay, now let's go back and look at this. So with a convex mirror, I know that I always have a virtual upright smaller image. And so that means that I can get rid of B and D, because these are both inverted. Likewise, if I had any values bigger than 1, I could get rid of them, because convex mirrors don't produce images with magnifications greater than 1. And so it has to be either A or C. And then I go through and I say, well, what is the focal length? The focal length is the radius of curvature divided by 2. It's also a convex mirror, so it's going to be negative 1 meter. Because the radius of curvature is 2, that divided by 2 is 1. And it's negative because it is a convex mirror. I also know that the magnification of a patient, I want to know the magnification of this patient, P is equal to positive 5 meters. Alright, so now I want to know the magnification, which is negative Q over P. I first have to solve for Q. So say 1 over negative 1 equals 1 over 5 plus 1 over Q. Bless you. Goodness. Goodness. You're welcome. So that would be negative 5 over 5 minus 1 over 5 equals 1 over Q. It's useful not to use your calculator. I find that I just mess it up when I put in my calculator. So if you can do that, that's fine. That's okay too. So that's negative 6 over 5 is 1 over Q. And so Q then is negative 5 over 6. And then if I want to know the magnification, I take this and I put it in for Q over here. And I find that the magnification is negative 5/6 divided by P, which is 5. And so that's positive 1/6, which is 0.16. Okay? There are lots of other examples of these, and I recommend that you work through them because they're all similar but a little bit different. So I would work through those and practice. Joy? For what now? Convex mirrors produce images with a magnification less than 1. And also, they always produce a magnification that is positive. Okay? Similarly, over here, if we wanted to put values to these, this concave scenario produces a magnification that is negative. This one produces a positive magnification, and also a magnification that's always bigger than 1. Let's see, this one up top produces a positive image distance. This one produces a negative image distance. Just knowing these types of images that are types of images that mirrors form will help you to answer some of the questions. You'll see what I mean. Can I go on down? We're going to do ray diagrams. Start on ray diagrams. We'll finish them up on Monday. Oh wait, no, what's today? Today's Friday. Yeah, we'll finish them up on Monday. So draw a ray. There are 4 rules for drawing rays. And you're not going to have to draw rays on the test, but I'll give you some questions with some correctly or incorrectly drawn rays, and you'll have to tell me which is correct or incorrect. So you draw a ray. The 4 rules is you draw a ray parallel to the axis, and it reflects back through the focal point. We've seen that. That's how we define the focal point, right? We can draw a ray through the focal point, and it reflects back on itself. Or, excuse me, it reflects back parallel to the axis. That's just the reverse of number 1. Rays have reversible paths. If they go in one direction, they can go in the opposite direction. We saw that with refraction, right? When it went from one medium to another, it would bend towards or away, and it worked in the reverse. We can draw a ray through the center of curvature. And it reflects back on itself. And then you can draw a ray to the center of the mirror. And the reflected ray follows the law of reflection, which is theta I equals theta R. You know, all the rays follow the law of reflection. They all follow this. But when you draw it to the center of the mirror, it's particularly easy to draw that ray so that the incident angle equals the reflected angle. All right, so you need to know how to draw these 4 rays for mirrors, and let's just start. So as I said, for concave mirrors, you can have the object be in 3 different locations outside the focal point. And remember, with that, when it's outside the focal point, I get a real, read that plus Q, inverted, and you can read that as minus M, negative magnification. You get a real inverted image. When I'm inside the focal point, I get a virtual, i.e. negative Q, upright, i.e. positive M, and bigger image. That means M is bigger than 1. We've already written that, but it's useful to rewrite it just to help you remember. And then I can be at the focal point, and no image at all. Okay? Want to draw the rays? They're kind of fun. Pull out all your pens, your different colored pens. Do you have your different colored pens? You know what I mean? My wife got me one of those. I like felt tip pens, and she got me the big rainbow pack. Oh, she actually got it from me and the kids, and then we got to pick like which colors we wanted. Kids, man, they always get what they want. I never get the colors that I want. They pick out all the good colors, and I just get like red and blue and black. And they get the yellow and the brown and the green and the... So she got some more. Alright, so outside the focal point, I draw a ray that's parallel to the axis and through the focal point. Through the focal point. That's close. That's number 1. Then I can draw a ray through the focal point and then parallel to the axis. That's ray number 2. Then I can draw a ray through the center of curvature and back on itself. I'm sorry, that's not very good. I'm going to fudge it a little bit, okay? It should work out, it's just I'm not being very careful with my lines. We're going to say the center of curvature is right here. It'll be through the center of curvature and then back on itself. If you're careful with this with a ruler, you'll find that the light rays will cross all at the same point. And then that's going to tell you where your image is. And then I can do a 4th ray. This one, by the way, is number 3. There are screencasts for this in your homework, by the way, because these are all homework problems. And then the 4th ray, I'll do in green, goes to the center of the mirror, and then it reflects back following the law of reflection so that these 2 angles are equal to one another. And so notice they all cross here at the same point. The reflected rays all cross at the same point. And then the image is going to look like this. Turn that frown upside down. Alright, so the image here is an inverted image. It's real. It's inverted and real. So it has a negative magnification and a positive image distance. Alright, if you want to look at the others, you can do so. They're on the homework. We'll do them on Monday, though. We'll go through them. But you're not going to have to draw the ray diagram, so don't think that. But you do need to know how to select out the correct or incorrect rays. Test on Friday, okay? It'll be in the auditorium, sort of normal routine. But make sure that you're prepared. Oh, and today is drop day. So if you're thinking about dropping, then please come see me.